All right, welcome back, class. This is 9.48, solving exponential and logarithmic equations. So what we're going to be able to do with all of our prior knowledge from the unit is be able to solve these functions. Solving exponential equations for b greater than 0 and b not equal to 1. If the bases are the same, b to the x equals b to the y, then x equals y. This is pretty intuitive. Like, let's look at this first one. If 2 to the x equals 2 to the 3, what does x equal? Well, clearly, hopefully it's clear that this will be 3. Because if we substitute x in, it's 2 cubed, 2 to the third equals 2 to the third. Yes, so we can evaluate exponential equations like that when our bases are the same. Evaluate a logarithmic expression. Round answers to the nearest hundredth. So again, in this case, when we have log base 3 of 8 equals x, we know that we can set this equal to x and go through like this, where it's 3 to the x equals then 8. Well, a property that we can now use is multiply by a log to both sides. So let me show you what that will look like. If I multiply the log on the left, it's now log base 3 to the x equals log base 8. And again, my common log we're using, or my base, is 10. There's an implied 10 right there. Now the property that we can use says that we can bring x out front, so that it's x times log of 3 equals log of 8. So I'm going to get rid of this here, because now it's log base 3 equals, or x of log base 3 equals log of 8. So what we're trying to do is find out what x is. So since we're multiplying, we're going to divide both sides by log of 3, so that we have x by itself. And now we have log of 8 over log of 3. Now I can plug this into my calculator and approximate what x equals. So we have log of 8. Oops, it wanted that there, so that's fine. Divided by log of 3. So it's approximately 1.89 to the nearest hundredth. And typically we'll want it in this form, but we're just showing approximations here for evaluating. Another way that we can evaluate this is using the change of base formula. So if you remember how it works, it's kind of a shortcut. If not, that's okay. You can use this route and it'll work out just fine. It'll work out the same way. So the property says if you have log base b to the x equals, well, the change of the base formula, an easy way to remember is that now your x will go on top, so it's log of x divided by b will go on the bottom, log of b. And that would be the change of the base formula. So in this case, b would be 4. So you'd have, let's see, x equals log of 15, which would be on top, divided by log of 4 in the bottom. And if you worked through it this way, the same way, you would end up at the same step right here. So it's a shortcut that you can use, but recommend using this route for at least the beginning. And then you can approximate that. So we have log of, maybe I can just steal this and change the values. Oh yeah, look at that. 15. Oh no, it didn't work. Well, too late. All right, I'll just plug it in. Log of 15 divided by log of 4 equals, we're approximating, approximately 1.95. That's an approximation. 1.95 is approximately what that is. Solve the exponential equation. Okay, so this is what we introduced at the beginning. If our bases are the same, they both have a base of 2, then our exponents must be equal to each other when we're evaluating. So we can set 6x equal to 3x plus 3 and solve for x. So we can subtract, not subtract 3 from both sides. We're going to subtract 3x from both sides, isolate the variable. So So we have 3x equals 3, and then we can divide both sides by 3 so that we have x equals 1. And if we substituted x back in, we would have 2 to the power of 6 for 6 times 1. And 2 to the power of 3 times 1 is 3, plus 3 is 6. So it'd be 2 to the power of 6 equals 2 to the power of 6. So that works there. This is my solution. Again, we have the same base, so we can set our exponents equal to each other. 2x plus 3 equals 4x minus 1. And now we can isolate and solve for x. So I'm going to subtract 2x from both sides. So we have 3 equals 2x minus 1. And then I'm going to add 1 to both sides. We have 4 equals 2x divided by 2. Maybe I should level off my steps here. So that then we have half equals x. And I hope that this is kind of making a little more sense as we build off one another. So our bases are not the same, but just like in that Unit 6 exam, we can manipulate our base to be the same. They have a similar base of 4. We can manipulate 16 to be 4 to the power of 2. So now it's 4 squared equals 4 to the power of x plus 1. Now we have a common base, so we can set our exponents equal to each other. 2 equals x plus 1. We're solving for x. I'm going to finish it over here, so then we have x equals 1. Let's plug it in. We can plug it in right at this spot, or that one. It would be 1 plus 1 is 2. That's 4 squared. Those are equal. And that looks good. Solving logarithmic functions. All right. For positive b, x and y, where b does not equal 1, if and only if x equals y. What does that mean? What does this abstract thing mean? Again, they both have a common base. Natural log has a common base of e. So you can set what's on the inside equal to each other if they both have that same base. Natural log of e equals natural log of e. So then we can set 2x plus 3 equal to 5x minus 6. And then solve for x. So I'm going to subtract 2x from both sides. 3 equals 3x minus 6. I'm going to add 6 to both sides. 9 equals 3x. Divide by 3. Over here then, x equals 3. And if we were to plug that in, you'd have the natural log of the same thing equal. So let me substitute. It would be the natural log of 2 times 3 plus 3 equals the natural log of 5 times 3 minus 6. This becomes the natural log of, let's see, 6 plus 3 is 9. This becomes the natural log of 15 minus 6, so natural log of 9. Yep. So that's all we're doing, substituting, and, well, at the end, we're substituting and checking to see if our answer is true. And that is an important step. We will want to check for extraneous solutions. Log has a common base of, maybe you're thinking in your head, what's the common base? 10. It's the implied base there. So these are the same base. They're both log functions or expressions here. So then we can set what's on the inside equal. X plus 3 equals 3x plus 1 and solve for x. Subtract x from both sides. So we get 3 equals 2x plus 1. Subtract 2. Oh, excuse me. I got ahead of myself. It will be 2 because we're subtracting 1 from both sides. And then divide both sides by 2 to solve for x. So 1 equals x. And that's what we would plug in and evaluate. And so you can check that one. Okay, now, since log functions and exponential functions are inverses, like when we have a product of something like 2x equals 4, we want to take the inverse to isolate for x, so we would divide both sides by 2. Boom, and get x equals 2. We can solve that one. When we have an exponent here, we can take the log of both sides, and then those are inverses. So let's do that. I'm going to take the log of both sides here with a common base of 10. Again, my property then says that we can pull x out to the front so that we have x times the log of 5 equals the log of 8. And now this looks familiar. We're solving for x, so when we have x times log of 5, we can divide both sides by the log of 5 and solve for x. X then equals log of 8 divided by the log of 5, which again we can approximate log of 8. Man, I almost feel like we did this. Can I not do it this way? Let me check. Oh, I hit clear, that's why. 5. It's approximately 1.29. Nice, that saved me some time. Which one do I want to do next? Let's do this one next. Just like when we have multiple step equations, if this were 2x plus 6 equals 4, we would subtract 6 from both sides to do the inverse to get 2x equals negative 2, so x equals negative 1. We're going to do the same thing here. We're isolating x, so we're going to do the inverse of adding a negative 6, so we're going to add 6 to both sides. So we have 10 to the power of 2x equals 152. Now I'm going to take the log of both sides. I'm going to write that down here maybe. Log of 10 to the power of 2x equals log of 152. We could go one of two ways here, but I'm going to show you and remind you that log has a common base of 10. The property says if you have log base b of b, it equals 1, because b to the first equals just b. That means that this simplifies to just 1 times 2x now, because 2x will be by itself, equals log, what would be base 10 of 152. And then one more step here, we could divide both sides by 2. So x equals log of 152 divided by 2. You can't simplify this fraction because it's log of 152. It's not just 152 over 2. And then we can round. We can approximate that. So log of 152, oops, I want to do that, divided by 2 equals. It's approximately 1.09. I actually knew that one off the top of my head. No, I'm just kidding. I didn't. Okay. Again, the common base for e is the natural log of e to the x. That's my common base. So we're going to want to take the natural log of both sides. E to the negative x equals the natural log of 5. That means, again, it's the same property, same base. It equals 1. So these will simplify to just 1, and we're left with negative x equals the natural log of 5. And I can go through that off to the side. If we have the natural log of b to the b, that'll equal 1 because, or should I say, yeah, e. That makes sense. E equals e, because e to the first equals e. So it equals 1 right there. This simplifies to 1 because it's a common base of e. All right, and then one more step. We need to divide both sides by negative 1 because we want x by itself. The natural log of 5 divided by a negative 1. Or it would just be negative natural log of 5. And I'll show you both ways. Natural log of 5 divided by negative 1 will be the same thing as the, I want that negative out front, natural log of 5. Those are the same. However, in this case, this would be the answer we're looking for, or x equals negative natural log of 5. That's kind of what we'd be looking for there. It approximated to negative 1 point, what was it, 6 something? 6.1. Again, in this case, we're isolating for x, so inverses. It's a positive 9, so we need to subtract 9 from both sides. Negative 4 to the ex, negative 4 times e to the x equals negative 4. So we can divide both sides by negative 4. Therefore, e to the x equals 1. That's a positive 1. You could mentally do this at this point. E to what power is 1? Well, we know any thing to the 0th power is 1, so you know x is 0. But let's just continue through and show that it's going to be 0. So the common base would be e, so we need natural log of both sides. So then we also know that this will simplify so that we have x equals the natural log of 1, and we can verify that that's 0. The natural log of 1 is 0. Look at that. Because when we substitute x for 0 right here, nope, one more down, right here, we would get e to the 0 equals 1. And that's true. Anything to the 0th power is 1 besides 0 there. So, all right, and then inverse operations. Up here we had exponents, so we took logs. Now we can exponentiate because we are given logs, so we want to take inverses where we take e to both sides. Excuse me, not e, our exponent. We want to take the common base to both sides. This has a base of 5, so I'm going to take 5 to this power on both sides. That then will simplify. Remember, that's the other property. When we have 5 to the log of 5, or b to the log of b, those simplify as well to just 1. Those were those inverse functions where when you compose them, you just get x out. Okay, so on the left, that means that these simplify so that we have x plus 2 equals 5 to the 6th, which 5 to the 6th is 15,625 equals x plus 2, and we're solving for x, so we're going to subtract 2 to both sides. Therefore, x equals 15,623. Nice. What's my common base? Natural log of what? What is it? I want you to think, pause it. Okay, hopefully you paused it. It'd be e. Remember, that's implied, so you're going to take e to that and e to the 5th. These have a common base of e, so that simplifies to just 2x equals e to the 5th. This is a irrational number because e is approximately 2.71, which goes on for infinity, so it'd be 2.71 to the 5th power. So before I round that, I'm going to divide both sides by 2 just to get x by itself. And so we get e to the 5th divided by 2 is approximately, I guess we can just check. Let's see, e to the x, so 5th divided by 2 is approximately 74.21 is what we would call that when rounding to the nearest hundredth. Okay, that looks like it. So it's a lot to remember, but there's a lot of similar concepts. We want to take inverses of both sides to simplify and solve for x. If we have a same base and we're evaluating, you can set the exponents or what's inside the logs to each other. So with practice, these will get better, and our next lesson, we're going to be doing more solving. So we're just going to do more practice and build up our comfort level. So thanks for watching. Let me know if you have any questions, and I'll see you later.